decision analysis, basically what we're trying to do is to take as many variables into account as possible in making decisions. If we're business decisions or safety decisions, these are the, that's probably value, better than values, I just realized that after all this time. Those are the things we kind of consider. What we want to do is to use what we have to avoid allowing it to be, allowing our decisions to be influenced by, as little influenced by biases as possible. You're always going to have bias influence you to a certain extent, but this allows you to minimize that by using standard techniques. This is this risk analysis. This is the most frequent way that this is done, and this is ubiquitous in industry. Everybody's seen this, where we have a matrix with risk versus outcome, or the probability versus outcome. I'm sorry, and then you take that and you try. I should have done this the opposite way, but they take this, and you have some sort of a, immediate action versus, you do it soon, but if you don't do it right away, you probably won't tell anybody or yourself, versus the other ones you can wait till time immemorial to get started on it. This, and the number of probability categories, the number of severity categories vary pretty substantially from one risk matrix to another. It's typical to have 4 or 5 to get resolution. The trouble with these is that they are good as a heuristic. They're good as a way to start thinking about, well, how frequently does this occur? If it does occur, what happens? And to kind of guide your thinking. However, I believe that industry, because of the intuitiveness and because of the ease of use, I mean, it's absolutely transparent. I think this is way overused. It's ubiquitous. We have it everywhere. And I think we rely on it a little too much. And from what I've seen, at least, the assignment of, whatever your categories are, but, your red, yellow, and green categories are more or less arbitrary. And because of that, I think that we overuse it and rely on them. I think it's possibly a good first step, but it's often the last step. And so I'm suspicious of them for that reason. I thought this was kind of interesting. This is from Roland and Moriarty. This is a frequency, in other words, how often it occurs versus the severity of it when it does occur. And this is a generalized curve. It's pretty much an inverse relationship, which, I can believe that. But they apparently had data specifically from air crashes. That's a curve there. They had human caused. This is the curve. Total human caused, that is. Fires, dam failures. So it's, this generalized curve varies quite a bit depending on what kind of a mishap we're talking about, what kind of a problem. So interestingly enough, that the frequency is much lower for nuclear power plants, and yet it has sort of it sort of rounds off before it hits a great number of fatalities, so it has a greater impact. Whereas these are far more common, but they reach this high impact in a more linear fashion. Anyway, like I said, I just thought that was interesting that they had collected enough data to assemble that for frequency versus severity. And to the best of my knowledge, this isn't categorized by anyone based on that kind of data. It might be better if it were, but it generally isn't. This is another one management and decision matrix that is frequently used. And it's just another example. Here they have specific numbers applied to probability, which you really need to do. You can't say it's going to happen often, it's going to happen less often, and it's going to happen infrequently, and almost never. That's not really meaningful. You have to apply some sort of an actual probability to it and base that on your data, to have it be meaningful. Here they have catastrophic, critical, minor, and negligible. Those also, this didn't happen to be defined, but those also need to have definitions associated with them. Catastrophic, what does that mean? Okay, how do we define catastrophic? Okay, so we have to operationalize the definitions of each one. And then they have a damage state associated with each one, which is really kind of superfluous. It's just shorthand. This damage state 1 just means catastrophic. And here in their matrix, they have A's, B's, C's, and D's as to what you need to, what the criticality is, for lack of a better word. And here they have the A's versus the damage state, and what you need to be doing. You know, a 3D and a 4D is out here. Means that you can probably go to sleep and not worry about it, whereas the 1, 2, and 3A's are the ones that are really bad. It's just another example of the same thing. This is a little bit better definition, but still, in my opinion, these things should be used with caution, more caution than they are, because they have a tendency to be not based on data, in my experience at least. So they're good to help your thinking, but don't over-rely on them. Another one, which is a little bit better, and I gave you 2 examples here, because I find the variation really interesting of event trees. And don't worry too much about, this is from Barr, what he calls barriers. And don't really worry too much about those. And by the way, the damage states here refer to what we had in the previous slide. But once again, that's not particularly important. Is that in each branch we have a success or a failure. And a success or a failure, success or a failure. What's interesting is they don't have this doesn't really add up. A success is the same probability as the event occurring to begin with. And then they have a negligible probability here. But this is still greater than that, probability of failure. So the fact that these don't add up to this, I find troublesome. Like I said, the only reason that I can think of for him taking that approach, and here, these two, the failure is exactly the same as this failure, then the success is some other number. So the source of it, because if there's only 2 outcomes, both of those outcomes should add up to the initiating event, as far as I'm concerned. Okay. And I really haven't been able to ascertain what method he's using to apply these numbers. However, let's assume that he's using a method that is reasonable. What he does is he multiplies through each of the branches. So this is this times this. This is the same as that. This is this times this. So you just have to multiply each of the probabilities through the branches, and then the damage state is based on something that we don't see in this diagram. We just know that it's damage state 2, 3, and 4. These are more severe, that's less severe. And here we have a cost associated with each one, and by multiplying the probability times the cost, we get a relative risk factor in probably millions or something like that. Okay. So even though this has a risk of high severity, it's very low cost. Whereas here we have a risk of low severity, but we have a value associated with it. This is, like I said, I find that this approach to it is a little bit, it's a little bit roundabout and obscure as far as I'm concerned. Another one from, appropriately enough, a Human Factors Handbook makes a lot more sense. Here we have an explosion, okay, and the frequency of that explosion. The probability of it happening from data is 0.8, probability of it not happening is 0.2. That's great, those add up to 1. If an explosion happens, a fire will start 80% of the time, not 20% of the time. But if a fire starts, the sprinkler system will work 99% of the time and not 1% of the time. If the sprinkler system does work, the fire alarm is activated that frequency and not with that frequency, and the same here, whether or not the sprinkler system works. And then it has the outcome for each one of these branches and the probability associated with it. And you can take that probability, and all you got to do is take this number and multiply it through by 0.8, 0.9, 0.999, and you get that frequency. If you have a situation where you can collect data or have data, even better, that you can fill out branches like that for, and then figure your frequency of your outcome, that is probably, I think, one of the best approaches to use. Whereas Barr's approach is, like I said, it's just a lot more obscure, and how to use the expected value here and the cost associated with it is, like I said, I find it less useful. Whereas this one is very useful and immediately interpretable. So those are some two approaches to event trees. Now this one I toss in here. I'm actually going somewhere with this. Has anybody seen the Drake equation before? It's one of my favorite ones. This is an astronomer, Frank Drake, back in 1961, came up with this probability of communicative civilizations on other planets. Okay, he said, well, to get that number, you would have to know, the rate of formation of suitable stars, the fraction of those sorts of planets, etc. Came up with all of these fractions, all of these probabilities associated with it. He said, if we knew those, and we don't, then we might be able to estimate, but the best you can do to get in is to estimate, is an estimate for that, because you really don't have access to a lot of those data. But you can estimate it. So it's it's an interesting exercise, but it gives you only an estimate at best as an answer. Now, from that, I came up with this, or found this risk estimate model, where you have the event, some initiating event, the consequence, what you lose, and what it costs. Then a way to model that, which is, to me, is an awful lot like the Drake equation, because you have the probability of cost per exposure unit, and the probability of the initiating event, which you may or may not have. You might have those two. Conditional probability of the consequence, given the initiating event. Conditional probability of the loss, given this conditional probability. So what they are essentially is nested conditional probabilities. And once you get to the bottom of this, you'll end up, I think, doing something similar to the Drake equation, where you might have an educated guess, but not a lot more. So I think to a certain extent, we can't be overly simplistic like we can in the risk analysis matrix, because that is not particularly supported. This would be great, but probably the best thing we'll get from it is an estimate, an educated guess as an outcome. So it might have the danger of giving false precision. And that's one of the problems that I wanted to emphasize for everything that we're going to be doing, everything we have done, is that because it gives you a precise answer, it may be misleading because it's only as good as the data you have to put into it. And these are great methods, but if you have bad data, you'll get a bad result. And this, all of these techniques are garbage in, garbage out. You have to have good data to begin with, or else it's not going to mean much of anything. And models like this are wonderful as long as you have good data to put into them. And you have to be very careful about that and very selective about where your data come from, whether you have collected them yourself, because if you collected data on your own, I mean, you can trust it because you at least know where it came from. So anyway, that's the point of this. Not so much that I want you to know this risk assessment model, but that I want it to be a cautionary tale. Yeah. It's
in the case of, like, your space shuttle example that we've seen a couple times, because it's just the one. Let's say you only have 139 missions or so. Are you basing your probabilities off of history, or are you basing your probabilities off of things like system reliability, known system reliability within the shuttle, let's say?
Well, the reliability, you can do it both ways. The way we did it, we're basing it on the overall history of the outcome of a launch, of a flight. If we're going to look at the system reliability of each aircraft, let's put it that way, then you would have to take the individual components, and you can keep getting more and more resolution and get quite a very, very complex model.
Right.
But ultimately, each one of those components is based on history, because that's how we learn the reliability of components, is you test them failure. Enough of them so that you have data where lambda stabilizes. That's the process, is to get, or the whole point of all these reliability testing is to get lambda to stabilize. And so if you believe that lambda is stabilized, then it's still historical in a matter
that's good
of thinking about it. But it's less the difference between historical and non-historical than it is whether you're doing it as a gross outcome of the action, or whether you're analyzing a subsystem of the entire system of an aircraft. So does that answer your question?
Perfectly.
Okay. Speaking of decisions, there are a number of methods that are called committee methods. In other words, a way a bunch of people can get together and talk about it and come up with a decision, and hopefully a good one. Okay, the first one is consensus. Okay, this is where we have a committee of people, and these numbers here, this is from Roland Moriarty. They think a good committee is 10 or fewer. That's their opinion. Okay, I'm not sure where they got that, but that's probably true, because if you have 50 people in a room, it kind of chaos. 10 people in the room might be chaos too, but it's less so. The more people you add, the more chaotic it becomes. So it's probably a good idea to limit it to something like that. And that's a good, I think, reasonable. You allow people to, it's sort of a, it's kind of a business rage in the cage, where you get everybody together and you find out who the natural leaders are, who the natural people are who are going to be speaking a lot. And so you allow that formation of factions and informal leaders, and you keep going until you get kind of unanimous decision. Now that, I think, is probably one of the weaknesses. He calls it a strength. You wait for a unanimous decision. I think probably that's a weakness because you may never reach that. I mean, get 10 people together to get them to have a unanimous decision about something is probably not likely. What you would have to do is probably do something like a majority decision. But anyway, he says if you do reach that, he calls it a strength, that it's time consuming, yeah, and that will take a long time. You don't know the decision will be reached, and that's just what I was getting at. You get enough people in the room, it's unlikely that you'll reach a decision, especially unanimously. And also, this is more of a test of social psychology than it is of accurate decision making. Because, yeah.
Is this basically describing a jury?
Other than the informal leaders, yes. Yeah, this very much could describe a jury. Yeah, because with informal, well, that's not true either. The facilitator is the jury foreman, and then the informal leaders are the ones that would arise in the jury room. So yeah, you're right.
I was just thinking of the movie 12 Angry Men.
Yes.
Like,
that's right. That's exactly
So
what this reminds me of too. I agree. And the social psychology of conformity is very compelling. And when you think about doing this kind of decision making, because there were some social psychology, the ones that I think are the most compelling to me are the psychology experiments where they had a committee, except everybody in the committee was a confederate of the researcher, except for one person, the subject. And they would, so everybody would agree on the most outrageous things. I mean, a line where one was 6 inches and the other one was obviously twice the length. And if they argued long enough and kept telling the subject long enough, it was amazing the number of them that would agree they were the same length. I mean, things that were obviously wrong, with enough social pressure, people will change their mind after a while. They'll convince themselves. So when it's something that's less obvious than that, I mean, when we're making decisions like decisions that have to do with safety and corollaries of that, this is probably not a good way to go, although it's probably the most common. I mean, it's the way our legal system works, as Taylor correctly pointed out. It's not necessarily the best of all approaches, but it's probably one of the most common ones because it's easily applied. But I think that needs to be used with caution. The next one that Roland Moriarty talked about is the parliamentary method, okay, where you have leaders that are either appointed or elected, and then you use something like Robert's Rules of Order. Okay? You guys all know what Robert's Rules of Order are, right? If you don't, tell me.
I do not.
You know, Robert's Rules of Order is a system of conducting, and once you hear it, you'll know what it is, of conducting a meeting where it's supposed to be in a more orderly fashion. That's where somebody makes a motion, and then for the motion to carry, it has to have a second or a third. They have to have an elected leader. No one can out-talk anyone else. It has to be in a very, very regimented fashion. That's the way that the meeting should progress. And then afterwards, after they speak, and this isn't that far from the consensus of the committee method, but after they vote on something, after the discussion, following these Robert's Rules of Order, then they reach a decision. According to Roland Moriarty, they always reach a decision. Well, probably if you don't let them out of the room until they make a decision, they will reach one. And maybe the jury system is kind of a combination between parliamentary and committee. But it's according to Roland Moriarty, and I don't see that this is any more the case of this than it is of committee method, is that this is susceptible to political maneuvering. Well, strength of personality is political maneuvering too, as far as I'm concerned, so it's just a matter of terminology. And also, if somebody voted against something, if they don't reach consensus, well, that's where it's different from the ideal committee system, where supposedly a consensus has been reached. then there will be resistance by people who were outvoted. And that's probably true. It's also true that if you're forced into a consensus, that you may change your mind later and resist it as well. So there's a fine line between this one and the committee method. Maybe at least the apparent orderliness of this might be the difference, and that's about it. So we have committee and parliamentary. A survey, this is kind of interesting, where you have experts, people who you believe are experts in the field, and they're surveyed. And then you tabulate the results, and you try to make sense out of those. Okay? That's assuming that they can be tabulated in any meaningful way. I mean, if you have a panel of experts that don't know each other, and they all render an opinion, they may be so divergent that you can't make sense of it. So that's a problem. If you know, all that effort is wasted then by using a survey. But it has potential for some success, I'd say. But you have to, once again, be aware that you might never get anywhere with it, that it might not be meaningful results. And then this one, like I said, Roland already say that this isn't the current news. I don't know that that's true or not. The Delphi method, and this was Rand Corporation that came up with this. Here you have a committee, but you keep them in isolation. They don't know each other. And you poll them for a decision. This is kind of like the experts too. And then you summarize the results, you send them back and say, this is what the committee thought. Okay? Then you poll them again, and you keep iterating until a consensus is reached. I don't know. To me, perhaps the strength, what this eliminates, this is kind of like the committee method without the strength of personality involved. It may be more of a dispassionate difference of opinion that each member of the committee can evaluate, look at it and say, I hadn't thought about that, and avoid the emotions that go into, that can go into trying to reach a decision when you're face to face with other people. So it may be preferable in that regard. And also, it's kind of a combination. Again, if you use all experts, maybe this might be a good way. And once again, these are things that Roland Moriarty said. I don't necessarily agree with them. He says that they think that 3 iterations is sufficient to reach a decision. I don't know. That would depend. Like I said, I think this is a lot more social psychology, industrial organizational psychology, really, as to whether 3 iterations. I don't know whether the data support that or not. I haven't heard about this being used very much, so maybe they're right, as it's not in current use. It's probably too much volume. My feeling is that in industry now, when we want to reach a decision, is we all get together in a room, we talk about it, because it's the most expedient thing to do, and it doesn't take much time. Whether it's the best way or not is questionable, but expediency and to a certain extent speed is very, very important. And Delphi and the survey method, this parliamentary method, all of them are more time intensive, probably more laborious to get to a decision than sitting down in a room taking your chances with strong personalities and people yelling at each other. The place that I used to work, was a large corporation, they used to, it was the funniest term for essentially screaming at somebody else in the meeting, and yet it was acceptable. And it was, to a certain extent, it was kind of encouraged implicitly, I thought. Constructive criticism. That was the term they used. And oh, what the heck? It doesn't matter. It was at Intel. I used to work for Intel, and it's a really interesting corporate culture there. In that it's most places they value in most corporate cultures that I've been exposed to, there's a certain value for discretion and keeping a cool head, for lack of a better term. You know, to try to be dispassionate and diplomatic in meetings. There it was just the opposite. Their corporate culture was going into a meeting and getting mad as hell and screaming at everybody, and then everybody felt better as far as they were concerned. and they actually promoted that corporate culture. It seems to work for them. What I think it does is that they self-select for people who prefer that kind of a environment. I didn't. Let's put it that way. I'm no longer there. But the people that were there seemed to thrive on it. So it's a self-selection process with a lot of places, I think. As is this. It's kind of a self-selection process as to what your corporate mentality is going to tolerate. So anyway, like I said, as decision methods, this is probably the most realistic, not necessarily the best. But I think we need to recognize that when we're making decisions, especially as a corporate entity, that very rarely do we truly speak from data. We like to as much as we can, but we're much more likely to use, you know, the psychology of interpersonal interaction as a basis for decisions than anything else.
What about the formal leaders? Like, basically, you're in that room with your, you know, the inner circle of the company or whatever, but you know, the boss is in the room, and you're all kind of subconsciously thinking, what does the boss want?
That's very true, and it's not only what he wants or he or she wants; it's what is the desire to operate within the boundaries that are set by the superior subordinate relationship. I mean, that's very powerful, and people are unlikely to challenge. I mean, to a certain extent, and it's becoming a little bit more acceptable to do that now than it was at one time. Yeah.
Very culturally influenced as well.
That's right, yeah. Because, and you guys know this better than I do, but from what I understand, in some cultures, cockpit dynamics are quite different. The captain is more, no matter how bad a decision it is, the rest of the crew is more likely to go along with it than in other cultures where it's acceptable to challenge the captain in the cockpit. And that's kind of just a microcosm of the entire culture, more or less. It seems to me, at least. So, any other comments or questions about that? Like I said, I think that's a good way to start out, because it's the way we tend to make decisions if we're honest with each other. Now, now we get to the ones where we have to be sure that we have good data. First method that I'm going to talk about is game theory. Game theory is part of operations research. It's a big field of mathematics, and it was first postulated in the theory of games and economic behavior by two mathematicians in 1953. And what they assume is that there are games, that we can model our behavior like we can model games, that two people or more play in order to maximize their benefit, their profit, whatever their perceived benefit is, and that there's a payoff at the end, and that's what players in a game are striving for, is to maximize the payoff. As part of game theory, and this is just a very small part of it, there are several approaches. And the first two, the maximum criterion and the expected value criterion, are sort of what's the best way to put this? The first two, maximum and expected value, are maximizing, getting the best outcome. Whereas the third one is called regret criteria. What you're trying to do is minimize how much you regret the decision that you made. And really, the minimax is the opposite of maximum, and the expected value of perfect information is the opposite of expected value criteria. They're virtually the same methods inverted. So I only include these just to demonstrate the relationship to the first two methods. And once again, I try to emphasize this in here, is it's really important to get valid data, and it's not particularly easy to get valid data for these kind of approaches. So, for these methods that I'm talking about, the first thing is to determine your alternatives. And here we have, as an example, 5 different alternatives. Okay. This is to allocate $500,000 for earthquake safety, $0.2 million for fire safety, $0.3 million for tornado safety. Second alternative is 0.2 fire, 0.2 tornado, 0.3 hurricane, and 0.3 for product, which is included there. Third one is all million for product. Okay, and then there's 2 more variants on that. So we have 5 alternatives. You need to, if you are going to do this, have alternatives that are likely and that are possible, and that each have some rational benefit. You can't put a straw man or a dummy alternative in there and have it and expect a meaningful result. They have to be alternatives that would be acceptable to the company that you're trying to decide among. So they're all realistic alternatives. Then you have events, and likewise these events have to be realistic. Okay. So here we have earthquake, fire, tornado, and hurricane events. Okay. And just I looked them up. I think these are the most recent. Maybe there's some of our the Richter scale for earthquakes goes from 2 to 8, 8 being the worst. Tornado, Fujita damage scale, F0 to F5, F5 being the worst. And hurricane is Saffir-Simpson, 1 to 5, 5 being the worst. Oh, you're the meteorologist. Do they still use those?
They do. The Fujita's now an enhanced Fujita.
Oh, it is. Okay. Does it still use F0 to F5, or is it something different?
Yeah, it's just a change of how they rate the damage.
Oh, okay. What is an F0 or an F2 is different. Okay. But it's basically something like that. Okay.
The Richter scale goes to 10 technically.
Oh, okay. But
if it does, it's bad.
It's beyond bad. Okay.
Yeah.
Okay. All right.
I think the worst one they had in Chile was something like 9.3 or something.
Oh, okay. Well, let me correct that. I don't remember where I got this, but I might have either it was a typo or I misinterpreted what I was reading. So okay, thanks. So anyway, these are once again realistic sets of events that we might realistically expect. Okay. Probabilities of them at this point don't matter. Right now, it's just a set of realistic events. So, and this is the difficult part. Here's our 5 alternatives. Here's our 4 events. What we have to generate is a matrix with some kind of utility. Okay? It doesn't necessarily have to be negative or positive, but it has to be a realistic utility scale. So if I chose A, what will be the utility of each of the 4 events? So, a good one, and these numbers I didn't make up, and I questioned some of the value of them, but let's choose C, which is $1 million for product safety. Okay? anything happens here, you know, I have an earthquake. If I have an earthquake, I'm screwed. If I have a fire, I'm screwed. If I have a tornado, anything that happens here, I'm probably done for. So my guess is that if I choose C and any of those events happen, I'm going to lose money. And so let's say that so I would expect a negative all through that. This doesn't have that. So I think that it's questionable, but like I said, I just wanted to go by an example that I had. This could be damage in millions of dollars, billions of dollars, millions of dollars, whatever. Whatever makes sense for the utility in there is an acceptable measure as long as it's consistent. Okay? It doesn't have to be a single digit that is some negative, some zero, some positive. Just be consistent with what's in the matrix. Okay. So, this is my matrix. In this instance, what I need to do is choose the alternative with the highest worst case value. In other words, what's the worst thing for each alternative? Okay, for alternative A, the worst thing is event 4, which was some combination. I forget what it was, doesn't matter. For alternative B, the worst case was event 4. For alternative C, the worst case was event 1. D was 3, and E was 3 also. So now we've decided what the worst thing that could happen, or the worst utility is for each one of my 5 alternatives. Okay. And in this case, using maximum, you choose the one that has the worst outcome, which is C. Okay, and the best one is E. So alternative E, this is pretty simple. Alternative E is the best because it's the one that has the best worst outcome. That's the best way to put it. Has the least detrimental worst outcome. That's pretty simple. Like I said, the method isn't difficult. Filling this, defining the alternatives, defining the events, and figuring out your utility matrix is by far the most difficult part here. Once you've got to there, this is trivial, but that's what you do with it. Maximum. Now, let's talk about expected value criteria. Let's take our same alternatives, events, and now let's say that we can assign a probability to each one of the events. And that would be good, because assuming that they are equally probable might not be a good assumption. If it is, that's fine, then we can stick with maximum, and we don't have to worry about it. However, if it's not, then we may want to apply these probabilities to each event. And that means that each alternative has an expected value associated with it. The expected value is pretty easy. It's the probability times the utility. So 1.3 is 0.3 times 2, plus 0.1 times -1, plus 0.4 times 3, plus 0.2 times 2. So you add all those up, you get 1.3. For B, it's 0.3 times 0, 0.1 times 1, 0.4 times 2, 0.2 times -2. Add them up, you get 5. Etc. Do that for each alternative. Now, with these changed probabilities associated with each event, it appears that alternative A is the best. If we made them equally probable, we would end up with alternative E, okay, which is what the maximum probably, which is what maximum would come up with. I would expect that. It just occurred to me to test that, so let's do that. expected value. Let's make these the same 0.25.
Yep.
Yep. And alternative B comes up as our best alternative. So, unless you think that for some reason there are different probabilities, you shouldn't even bother with this. But if you think that there are different probabilities for your 4 events, then this is then the expected value criterion is the best one to use. Okay, like I said, Minimax is a, I'll call it pessimistic version of Maximin, and expected value perfect information is a sort of a pessimistic version of expected value criterion, because it will give you the same result, and it's recognizably the same. And it's more complicated on top of that. So it's an added benefit. Minimax. For each event, now we're talking about events. For each event, choose the best value for each event. The best value for event 1 is 2. The best for 2 is 3. The best for 3 is 3. And the best for 4 is 2. There's 2 of them. So you've got two best. Then you subtract every matrix. You subtract that every matrix element from the best for that event. Okay, so this is 2. The best for this event is 2. So it's 2 minus 2, 2 minus 0, 2 minus -3, 2 minus 1, and 2 minus 1. Here, this is 3, so it's 3 minus -1, 3 minus 1, 3 minus 3, 3 minus 2, and 3 minus 1. And same thing here. Okay? So, using that, you choose the highest values for each alternative. Or the lowest value, because once we've subtracted off the best thing, the best value, the worst, and given the best value, and you subtract off what the utility, this is the one, this is where we minimize our loss. And you minimize the loss by looking at the alternatives, and here, as it turns out, it's alternative E as the lowest value. So we're looking for the lowest value here. Same result. A slightly more complicated way to get there, but it gives you the same result. So that means that it has the least regret. That's why I said these are regret criteria. So I only regret 3 units of utility versus 5 units or 4 units of utility.
So, if you chose C as an alternative and event 1 happened, you would have the most regret.
That's correct. Yeah. Whereas the least regret that I can experience is if I choose E. It's still some regret, but it's not as bad as C. Everybody with me so far? It's just add, subtract, multiply, and divide. And like I said, the result is exactly the same as maximum. Expected value of perfect information is to take our minimax, matrix. This is the same matrix where this is our regret, and you multiply it by the same probabilities for each of the 4 events, using the same technique, 0.3 times 0 plus 0.1 times 4 times 0.4 times 0 plus 0.2 times 4. And here, again, we look at the lowest value, because that's the lowest loss. And it gives you the same result. Expected value of perfect information allows me to minimize my regret. So these both are based on the regret matrix, and we want to try to minimize it as opposed to maximizing utility. But it gives you the same results. I just wanted to show it to you for comparison purposes.
The same result in
For
for what?
As the expected value of perfect information gives you the same result of the expected value. And
okay,
gives you
okay.
A.
Got it.
And the maximin and minimax give alternative E as the choice.
Oh, okay.
Any questions? Like I said, it's more the idea of it, because the arithmetic isn't difficult. And again, to emphasize, what is difficult here is defining the alternatives, your events, your probabilities, and the utilities associated with each. And that requires knowledge of your system, knowledge of your industry, whatever organization, whatever that is. It requires a lot of knowledge to be able to assign that meaningfully. Okay. Well, why don't you, since it's almost 4:30, I've been yammering for an hour and a half almost, why don't you take 15 minutes and then we'll come back and finish up what we'll talk about today.